Hello everyone. In this lesson we're going to be continuing with the overall topic of trigonometry, and specifically we're going to be talking about an application of trigonometry called angles of elevation and angles of depression. So in this lesson we're not really going to be learning any new math, but we are going to be working with an application of the math we've been learning. So application as in a topic or way in which trigonometry might show up or might be useful in real-world situations. So, what is an angle of elevation? Well, it's probably easier to illustrate. So here's an example. A construction worker looks up at the top of a building. The angle of elevation is 60 degrees from the horizontal, as in from the worker's eye level. So in general, an angle of elevation is the angle that you're looking up at. What do I mean? And in general, you're going to want to sketch these situations and sketch them as a side view. So looking from the side, here's our worker. And he's standing on the ground. And then we've got the building. And he's looking up at the top of the building, right? So he's looking this way. And so what's the angle of elevation though? Where does that 60 degrees go? So first off, it's important that you know what the horizontal is. And the horizontal means where the worker would be looking if he was looking straight forward horizontally. So if he was standing naturally looking forward, then his view would be going this way, right? So this dotted line is what we would call the horizontal in this situation. But then he's not looking forward, right? He's looking up. Maybe he started looking forward and then he turns his head up to look at the top. And this angle is how much he would have to turn his head, right? So that angle right there between the horizontal and where he's actually looking is this angle of elevation. And in this case, I guess the angle is 60 degrees. So again, the angle of elevation, it's the angle that we're turning our head up to look at something. So now, what is an angle of depression? So first of all, know that an angle of depression has nothing to do with the psychological state of being depressed, okay? And angle of depression is just like angle of elevation, except for looking down. So here we have an example. Sammy is on the upper level of a lighthouse, 80 meters above sea level. She sees a ship out in the distance at a 7-degree angle of depression. So here's a lighthouse. And it must be on some land. And then here's the sea. And then there's a ship out here. And we're zoomed out quite a bit. So let's just say Sammy is this dot, in the lighthouse. And again, don't forget about the horizontal. If she was looking straight out, then the horizontal would be here. But then she's looking down at the ship. So here, looking at the ship. And the angle of depression of 7 degrees, she's looking out would be the horizontal and then down. So this angle right here is 7 degrees. That's the angle of depression. And so in this lesson, we're just going to do some problems that involve angles of elevation and depression, and we will find that they involve this SOHCAHTOA we've been working with. So here's our first example. It says, suppose Anna is standing in the street in front of her building, 26 feet away from the base of the building. Her angle of elevation to the top of the building is 52 degrees, and her eye level is 5.5 feet above the ground. What is the height of the apartment building? So it's really going to benefit us to sketch the situation, okay? And like I said before, we're going to make this a side view. So here's Anna. And actually, this situation is very similar to one of the situations we discussed earlier. So Anna's standing on the ground. She's looking up at the building. And then it says she's standing in the street in front of her building 26 feet away from the base of the building, as in from the bottom of the building. So that's this distance right here is 26 feet, right? And then her angle of elevation to the top of the building is 52 degrees. So we got to sketch that. And again, don't forget, let's draw the horizontal here, as in the direction she would be looking if she was looking straight forward. And then the angle of elevation, that 52 degrees, is she's looking up at the building like so. And this angle of looking up is 52 degrees. And her eye level is 5.5 feet above the ground. What does that mean? So that's this distance between her eye and the ground. So this is 5.5. Although that's getting kind of crowded, so let's draw that over here instead. So we've labeled all the given info in the problem on the diagram. But what's our unknown? What are we being asked to find? It says, what is the height of the apartment building? So that's like this distance, right? Or even like down the middle, the height could be there or there. But what you have to notice here is, so first of all, if we're dealing with vertical things like that building, or horizontal things like the dotted line or the ground, unless they tell us, we're gonna assume that they're totally vertical and totally horizontal. And if you think about it, that means those totally vertical and totally horizontal things are perpendicular to each other. So the apartment and the ground, perpendicular as in they're at 90 degrees here. Or more importantly, the horizontal and the building, they're perpendicular, they're at 90 degrees there. And now if you look, you'll see that there's a right triangle in this situation, and that means we can do SOHCAHTOA with it. Where's the right triangle? Well, it's here, right? Boom, right triangle, triangle with a 90-degree angle. And now we're trying to find the height of the building, which is this whole length right here, right? But notice that our right triangle, that side length here doesn't go down that whole length. So what we're going to do is we're going to do some math with the right triangle and then do some stuff later to get the whole length. What do I mean? So let's clean this up a little bit. So first of all, we're trying to do SOHCAHTOA on this triangle, and this triangle has no side lengths. So we have to think where we can get some side lengths from. And if you notice, this length on the ground, 26 feet, should be the same as this length right here, right? Because it's just that same length moved up a little bit. So this should be 26 feet as well. And then we said we wanted to calculate the height of the building. That means we're going to have to be working with this side length because that's related to the height, even though we're missing a little bit down here. And so for now, we'll just say this length is our unknown. We'll label it with an X. And now we've got all the pieces we need to do SOHCAHTOA. Because look here, let's separate this triangle out from our sketch. So like if I draw it separately, then we have a right triangle like this. 90 degrees is here, 52 degrees is here. This side length is 26, this side length is X. And now SOHCAHTOA. What are these lengths relative to the angle? Well, we're not working with the hypotenuse. X is across from the angle, so this is opposite. 26 is adjacent. And which ratio uses opposite and adjacent? That's tangent, right? So we can set up an equation. Tangent of the angle, so 52 degrees, equals opposite over adjacent. So x over 26. And then if you multiply both sides by 26, you'll get x by itself. So x is 26 times whatever tan of 52 is, and you can even write it like this, 26 times tan 52. If you stick that in your calculator, you will get around 33.2785. And this is like a real world situation, so don't forget, what are the units? Well, we just found a side length, and for our lengths we've been using feet, so x is around 33 point something feet, right? And now it looks like we found our final answer, but notice, we're actually not done. This length that we found is this right here, right? This is 33.2785. But that's not the height of the building. We're missing a little bit down here. And so what is that little bit down here? Well, if you look, this is the same as the eye level on the person, right? It's that same distance except transferred over here. So we can say this part is 5.5. And now the final answer, the total height of that building is this 33.2785 that we found on our right triangle, plus the extra from the person's eye level. So the final answer, the height of the building, is around 33.2785 plus 5.5 for a total of 38.7785 feet. And that is the final answer, because that's the height of the building. Now, here is our second and last example for this lesson. And it says, a salvage ship's sonar locates the wreckage of a sunken ship at a 12-degree angle of depression. A diver is lowered 40 meters to the ocean floor. How far does the diver need to walk along the ocean floor in order to get to the wreckage? So again, let's do a sketch. So a salvage ship, right? So that ship's on the surface of the ocean. Here's the ship. And then a diver is lowered to the ocean floor. So here's the ocean floor. And this is rather unrealistic, but for our purposes, we're going to assume that the ocean floor is totally flat. And then here's the diver lowered on a line right here. And then there's a wreckage of a sunken ship on the ocean floor. So let's say around here. That is quite a wreckage, wow. And then the angle of depression from the ship to the wreckage is 12 degrees. So the horizontal, let's say it's looking out this way. And then it's looking down like this at the wreckage. So this right here is 12 degrees. And you really have to be careful because angles of depression, it's really easy to get different angles incorrect. So again, this one is 12 degrees. And now we have to think, like, where is the right triangle here? So like we've got a vertical side here and a horizontal length here. And by the way, it says the diver is lowered 40 meters to the ocean floor. So this right here is 40. But then this side length is on a triangle that does not involve this angle that we're given. So you may even have to draw some extra lines. Like we could draw an extra line here, and that distance should be the same as this 40 over here, right? If everything's horizontal. So we could say this is 40, and then we could say this is 90 degrees. Also, what are we trying to calculate? How far does the diver need to walk along the ocean floor in order to get to the wreckage? So that's this distance right here. So again, it's strange. We've got a right triangle here with side lengths, but no angle. And then we've got a right triangle here with angles, with an angle and one side length, but the unknown's not on that triangle. So again, what you have to do is you have to really be careful where you put the side lengths and where you put the angles. And you can do it with either triangle here. If you wanted to do it with this triangle, then you can say, well, this distance on the ground should be the same as this distance up here because it's like a rectangle. So boom, we could put x there, and now you have this right triangle that you could do SOHCAHTOA on. Or you could be like, well, these should be parallel. So this angle is alternate interior with this, if you remember properties of parallel lines from your previous work. So alternate interior angles, that means this is 12 degrees. And then you could use the right triangle down here. Or you could even say, well, this right here is a total of 90 degrees. And if we're using up 12 degrees here, then there are how many degrees left out of 90 there? 90 minus 12 is 78 degrees. And now again, you can do SOHCAHTOA with this triangle. So it's kind of overwhelming, but the point is there's many different ways that you could do this. And even though those ways are different, you'll still end up with the same distance for the x here. So I don't know which one makes the most sense. So I think I'll just go with the first triangle that we had. And we'll say, okay, if this is 40, then this over here is 40. If this is x, then this is x as well. And now we can use this triangle to calculate x. If you draw it separately, we have 90 here, 12 here, x there, 40 here. Actually, again, it's tan. 40 is opposite, x is adjacent. And then tan of 12 degrees is 40 over x, opposite over adjacent. And then multiply both sides by x so that we get x out of the bottom of the fraction, the denominator, so get x out of there. And then we have x times tangent of 12, which is around 0.2126, that's around 40. And then divide by that, right? 0.2126, 0.2126, these go away. And so you have that x is around 188.1852. And again, the units, we're working in meters here. So 188.1852 meters. And is that the final answer? Yeah, unlike the last problem, that's the exact distance we were looking for. So we're done. That is the length or the distance that the diver would have to walk to get to the wreckage. So that's it for this lesson. Again, be careful with angle of depression because it's easy to mix up the angles and such. As always, if you have any questions or feedback, feel free to contact me.